So we are going to be looking at notes pertaining to graphing functions. So what you're going to want to be able to do is hopefully you have at least 3 sheets of paper and going over some really fundamental and essential notes when it comes to just graphing and graphing function in general. So to start off, we have our fundamental equation. So this equation or version of it is going to come up over and over and over again when it comes to making graphs of functions. And so one thing to note is even though this is a primary one that you're going to see in the book, alternate forms that are the same. So these mean they don't change the graph at all. They're just different ways of writing the same thing, kind of like equivalent fractions or anything along those lines. So you could see this as g of x equals the absolute value. Notice here that the a is basically times the 1 over b inside the parenthesis, or excuse me, the absolute values. And then that could still have the plus k on the outside. Or you could also see it where it has the b on the outside of the absolute value in the denominator. So it is really important to acknowledge that you can rewrite this equation to either look like this one or this one, depending on kind of what you're doing and what's easier for you. Personally, I kind of prefer this one here in terms of thought process. I will be using a bit of this one because that's what oftentimes is in the book, so I'll make sure it's there. But we have the example. Let's just say your A is 2 and your B is 3, so it's 1 over 3. So you could basically, again, 2 times 1, you can either have the 2/3 on the outside of the absolute value and the x minus h on the inside, or you can move the 2/3 into the absolute value and think of it that way. All 3 of these are identical forms of each other, and you can swap any direction you want. But there's a bit of information that you want to make sure that you pay attention to. If in this situation your a or your negative, your 2 here is a negative 2 or negative a, then you have to think about that as -1 times 2. And what that then becomes is we can suck the 2 into the absolute value, but the negative has to stay on the outside. That comes back to, we want this to be a negative graph, a downward sloping graph. And if we move that negative onto the inside and then take the absolute value of it, it's going to become positive. And that's going to give us a totally different directional graph than what we want. So make sure you have that note. If you have anything that's a negative a, that the -1 stays on the outside, and then you can bring the a on the inside. So since we have a formula, a fundamental formula that says x minus h, no matter what h is, if h is positive, then x minus a positive 3 is going to give you just what you have here. But let's say if h is -3, this negative still is part of the initial formula. It's minus whatever h is. So if h is -3, then it's minus -3, or what you have here, which a negative times a negative gives you a positive. So this is really essential because this gets a lot of people, myself included sometimes, of having to remember which direction that is referring to. But if this actually has an x minus a number, that actually means your h value is positive. If it says x plus a number, then that actually means your H value was a negative number. So if you need to, put a little extra star next to these, and feel free, because that's going to become important when it comes to graphing our equation, is to recognize that the actual value of H is going to have the opposite sign of whatever is inside the parentheses next to X. Okay. So here's a little bit more of that detailed information. Thus, X minus H has a positive H and is also a horizontal shift to the right. So this is moving the graph to the right a certain amount of points. And if you have a positive H here inside your parentheses, or should I say plus, then your actual H itself was a negative. And thus is going to move it to the left. So if you have something that looks like this inside your graph in your absolute values, then that's a +4. And that means that your vertex needs to at least move over to the right 4 times. Horizontal shift to the right. If you have something that looks like this, that means your vertex actually has a -4 X value, is going to move over to the left. So feel free to pause these whenever needed. So graphing functions, part 2. Most people are familiar with the point slope intercept, the slope intercept form, which is the y equals mx plus b. Y is your output. It's what you get after you input x and put it through all this operations. M is your slope, which if you remember is oftentimes represented as a fraction of rise over run. And b is your y-intercept, or when x equals 0, where does the y cross the line? The point along the y-axis. So this hopefully is review if you are in Algebra 2 of the fundamentals. So here we have just an example of our 2/3 x plus 1. So that means I went up by 1, and then I had a rise of 2 and a run of 3. And that gave me my next point along my linear graph. So this is perfect for linear or line graphs, which are basically when your exponent is a 1. The little number that should exist here, but it's invisible because it is a 1. But what you're going to see is this new equation that we're working with is actually really similar and almost identical, that's the similar, to the slope intercept form. It basically is the same thing, but they wanted to change things up and, well, make things more complicated. So let's look at this. So y and the g of x are both your outputs. Those are identical. They're the same concept. M, remember we can write this a as b over 1, or we can write it as a over b out here, or a over b inside from the previous page. But if you notice, it's a fraction, which is what is equivalent to our slope, or what we're going to do in terms of a rise and run to find our next point on the graph. Okay, rise and run. This concept is going to be the same as to where is our next point on the graph, given our vertex or our starting point, which comes back also a little bit on B. B indicates how much the graph moves up. Well, K is the equivalency of that. This letter out here represents any number, tells us whether we're moving up or down in our graph. So the only thing that's really kind of different or new, besides obviously they're using different letters, is the fact that we now have an H and a horizontal shift ability And a lot of that comes because with the linear line, even if I move it to the left, I simultaneously are moving it up. And if I move my graph to the right, I'm actually simultaneously moving the intersect down. So instead of worrying about the left and right on a linear line, they only pay attention to the up and down. And so the h is just always basically 0. And that's what you'll see here. The y-intercept, this is really important, because if you understand that all three of these things are very much the same concept, it makes life a lot easier. The y-intercept, the line of symmetry, and the vertex are initially all the same thing. The y-intercept concept on a linear line, which could technically be a line of symmetry, but a line extends on forever, so it's kind of the middle point is kind of a mute point. But a line of symmetry and a vertex comes highly into play when working with graphs that are not linear. Anything, but they're initially the same thing, because I can rewrite any linear equation with an h, x minus 0. And what that becomes is my y-intercept then becomes the point 0b, or technically hb. It's the same thing. Over here on this graph, that concept still exists. We are going to find our vertex, which is the lowest or highest point, or the point where things change. If you notice from here, this is a downward slope, and then all of a sudden it becomes an upward. That's where vertex, all the action and all the change happens at the vertex. And a line of symmetry comes from the fact that I could put a mirror here and both sides would be the same. And this little vertex point here originates from the value being subtracted from the x, just like on my line, and the amount my graph is being raised or lowered, just like on my line. So the y-intercept concept is not a new concept, nor is this vertex. So whatever h is, now remember, if it's a minus, that means h was a positive. If there's a plus here, that means h was a negative number. But this and this is your point here, and your line of symmetry and vertex. Highlight star, huge bit of information, makes life so much easier. You can literally look at the graph and go, well, there's my x, there's my y, and that's my point of my vertex. And then things build off of that, which we'll get to. Okay. Make sure you pause it as needed. So graphing functions part 3. This is just page 3 basically. So when I talked about the slope, and that's what m is, the same thing exists no matter the type of graphs in one form or another. And so what I've done is I've created a page of the different types of graphs that oftentimes you'll see. Obviously, you start off with the fundamental linear equation and linear function. We have our y-intercept, we have our slope, and our slope tells us where we would find our next point. That's what it is. It's going to be my rise over my run. That's my m. If we're working with absolute values, then again, my vertex is going to be found from my h and my k. And then my first initial point is going to be composed of my rise and my run. That's my slope. So that tells me how steep it is, or how wide it is, or just a 1-to-1 ratio if there's nothing there. And then since these ones bend though, because they're absolute values, so they refer to all positives, you're going to go up and backwards to find this next point. Kind of like over here, you would go backwards and down to find these points here. You're going to go up and back, up and forward, same quantity, thus the line of symmetry. Because all of these points here are going to be identical in distance from this central point here that runs through the vertex, which is your line of symmetry, which is your H and your K. Because that's your horizontal shift over, in other words your X, and your rise, in other words your Y. So even in parabolas, parabolas happen when your exponent is squared. And so as you see, we no longer have absolute values, but we now just got parentheses going on. And this is what's called a vertex form for parabolas. There's a standard form and there's a vertex form. But you'll see it looks very familiar. My vertex, or my minimum or maximum, in this situation it's a minimum because it's the lowest point on the parabola. If I had a negative parabola and it was coming up from the bottom, then I'd have a maximum, which is equivalent, again, to my vertex. And that's composed from my rise, which is my A, over my run, which is my B, to get my next point in either direction. And then the parabola is a curve going up if your A is positive, down if your slope is negative. And your vertex is again composed of your H and your K. So even if we had a cubic function, which the vertex is the point of change. If you notice from here, again, it's kind of going one direction in our graph, and then our graph flips and starts doing something different at the vertex. You see that it's raised to a third root, thus the cube. Cubic means raised to the third power. And if I was to graph something like this, at least in this form, I have my A, which still represents the rise, and B, which represents the run, for my next point on the graph. So obviously I'd go down and back to find the next point in this. And my vertex is once more my H and my K. Please note, if this was an X plus H, that means my actual H would have been a negative value, and I would have gone back and then up to get my vertex, and then constructed the graph. If this is a negative K, well, that means I'd go down, and then that'd be the points down to plot my vertex, and then do the same rise and run from there. This is called translation of a graph, is the shift, horizontal and vertical shifts of it. We're translating it, moving it across. So we're going to get into these, but I also want to make sure you have them under your graphing functions notes of a simple rational. And this graph here looks a little bit more intimidating because everything's over 1, but initial still components exist. Where this is my X and my Y axes, we'll have two asymptotes, which we'll get into those, as to points that the line never crosses. And that itself still has a central point. And this central point moves, and the whole thing moves, but it moves in reference, again, to the H and the K. Again, we'll explain this more in detail later, but I want you to be able to start looking at the patterns and recognizing it and seeing how they're all connected. And then even from there, my A and my B still help indicate where this first point is in both directions that the rest of my graph is then built off of. Square roots. You'll look something like this, of a times the square root of 1 over b times the difference of x and h. Okay? And then plus k. H and k still refer to my starting point. B, A and B are still my rise and my run to find my first point, whether it's down lower and kind of more of a small hill, or if it's up higher in a steeper hill before it shoots off for this square root graph. So those are all three parts and go over at least in this video. And it's again essential to notice that the faster you pick up H's as my horizontal shifts, and they go the opposite direction than whatever is inside these signs. K is my vertical or up and down shift. If it's positive, my vertex goes up. If it's negative, it would go down. And A and B help me find my first point to build the rest of my graph off of by being my rise and my run. So as long as you can again come back to the concept of y equals mx minus 0 plus b, and that's initially what we're working on. That's what all these are rooted in, this fundamental equation, in the same basic process. All right, I hope this helped.